Sorry, she doesn't hate you, she just thinks you're flippant. She's just nice. Are you gonna yell it out once we write it?
Okay, today's concept is work. Do me a favor. If you don't care about my class, you don't want to pass, enough to be quiet, leave now. I already have my grade. I have my grade, Ms. Gamboa, we got our grades. I'm out of here. You guys need a grade if you want to pass, which means you need to hear what I'm saying. So we have a short lecture. Fill this out as we go along. It's the way the body works. If you're talking, you're not listening.
Mr. Cook?
Yes?
Are you going to do it in order?
I'm going to do it in order.
Pay attention.
You're just going to go down. This is your formula sheet. It's going to help you get through the assignment. It's going to help you get through the reading. Now, quick review. When we're getting into work, work is a measure of energy. And there's a couple concepts we're building on. Like most classes, we sort of build on stuff. Previously, when we went through all of Newton's law, we talked about a concept of force. And we came up with a very simple definition of force. What is force? Anyone remember?
Pull or push?
Pull or push. Awesome. Pull or push. Now, if I pull an object or push an object, what does that object do?
Fall, because of gravity.
Falls because of gravity and what other stuff? Gravity is the force pulling down. It moves. It's no longer stationary. The idea of something moving is going to play a very important part in the physics concept of work. We use work in everyday vocabulary, like I go to work. Not exactly the same thing. Remember, we're going to come back to the idea of something moving. When we measured force, what was force measured in?
Newtons.
Awesome. This should be really simple. It's measured in newtons. Big capital N. As part of the formula, as we calculate work, we're going to be using a lot of newtons. We're going to work on the force pushing on something. When we were talking about force, we often had stuff, remember basic newtons. We had force equals mass times acceleration. And with this formula, we could figure out forces of stuff on Earth because we knew what the acceleration was. The acceleration was our gravity. And it had a very specific value. Do you guys remember it?
9.82.
Yes, 9.82 is correct. This is good enough for high school. And it's a form of acceleration that was meters second squared. But this is an important number because occasionally we get a trick question when we want to use it.
It's meters per second, right?
Meters per second. It's a form of acceleration. This is the acceleration. And remember, in physics, our unit for acceleration is meters second squared. And why I wanted to review this is because in some of the questions on work, they will often give you the mass of something. You'll be given mass, but you'll want force. So if I have something that is, say, 10 kilograms, which is mass, what would I do to it to turn it into a force?
Mass times, I think, acceleration.
Which is, we just did the number.
9.82.
Okay, so if I take my mass and I multiply it by 9.8, yes, 9.8, whatever my number is, that's going to be in newtons. That's going to be my force. A simple conversion. So quite often when you're doing work, instead of saying you have so much force on something, you will say you have an object that weighs 10 kilograms. Well, to figure out the force on 10 kilograms, you would just times it by 9.8. Quick review on that. Come on, little board, work with me. Long ago, we talked about standard international units. What is our unit for distance? When we measure something in physics, we always tend to give it a certain ending. Distances would be stuff like miles, meters, inches, yards. What do we use in physics most of the time?
Meters?
Yes, meters. So when I ask you to measure something in physics, unless I specifically say use another thing, you will give me the measurement in meters. If I say how big is it, you say 9.2. My assumption as a scientist would be you're talking about 9.2 meters. If I'm smart, I would double check. But the idea is you give me measurements in meters unless I ask for something else. However, when we use our meter sticks, since this is 1 meter or 100 centimeters, we tend to measure stuff a little smaller. We tend to measure it in centimeters. And we'll say it's like 50 centimeters. So how do I convert centimeters to meters? Anyone want to take a wild guess? I have a
I wanted
number.
to say 12, but that's, I'm thinking of the wrong now. I know, I'm thinking wrong.
Okay.
Keep thinking.
There are okay. 1 meter equals 100 centimeters. So there's two ways, just two simple mathematical ways that we can do it. We can do what we call our cross division or dimensional analysis in chemistry, which would mean I would take my number in centimeters, I would multiply it by 100 centimeters over 1 meter. My centimeters cancel out, and that'll leave me with some number in meters. If that is too complicated to remember, some people like doing it this way, and by far, if you're going to do a bunch of stuff, this is the one that will give you the less mistakes. The other way is take your number in centimeters and simply divide it by 100. And that'll give me your number in meters.
I'd rather do that one.
Or centimeters divided by 100. Simple conversion.
Hey, mister.
So 1 centimeter would be 0.01 meters.
So centimeters divided by 100 would give you the meters?
Correct. Converts it into meters. Like if I take 10 centimeters, I divide it by 100, that would give me 0.1 or 1/10 of a meter. Everybody caught up on so far?
You did that all. Oh, I thought it was
So, our word of the day, work. This is our big concept. You want to know what work is? Work is the energy simply the energy needed to move something. Move something. I was one of those who always get near the end of the paper and have to make the words really, really small.
I was the same way.
So it's the energy needed to move something.
Energy need. Is it hard for you to write on the whiteboard?
No, it's actually pretty easy to write. I'm actually heavy-handed on the whiteboard. I'm pressing a lot harder than I need to. Because I'm used to chalk, where the harder you press, the cleaner the line is. In this, if I do it really lightly, it makes the same line as if I push it really hard. But I'm just so used, I'm an old guy, I'm used to chalk and pencils. I'm used to using charcoal on our cave drawings when me and the other cavemen sat around and told stories. And chisels.
You know, I used to think that they would use their own blood to write the stories.
So here's a couple things that are important about work. I mentioned it's energy needed. And remember, I can't spell today. Remember last time we were doing our little net forces, we would put we would put forces on the blocks, and the block would end up moving? This is sort of what we're talking about. We're going to calculate the energy behind that. And last time we discovered we could get lots of different forces on an object. One of the concepts you have to remember is not all forces are important to find work. So,
is that for the next one, mister?
Yeah.
What is the importance of force?
Correct. Not every force on an object do we care about when we're calculating force. So part of the puzzle in figuring out work is eliminating those little arrows you don't need, the forces you don't need. And we're going to get into that. Everybody got this?
Yes, sir. No.
So
just get the idea that not every force is important. If I can have a force pushing up, a force pushing to the right, a force pushing down, a force pushing to the left.
So we're about to discuss the one that says what is a relationship between work and direction?
Yes, we are. So what's important in work? The important force is the one.
Is that for the next one?
Yep. The one in the same direction. Same direction as object moves. Example, if I have force pushing a box.
May I close the door and check my
Yeah, and my box is moving this way. That would be the important force, because that is the force in the direction of the movement. This may become an important concept in work. The force must be in the same direction the object is moving. If I have a force going upward, this one is not important because it's not in the same direction the object is moving. You guys got this?
Yes, sir.
So, here's our big formula. Here's what you guys have been waiting for. Work equals force times distance. Usually expressed as work equals FD, force times distance. Now, thinking back earlier, what is my unit for force?
Newton.
Okay, what is my unit for distance?
Meter.
Okay, so it's going to be whatever has an N after it is my force. Distance. Now remember, if I have this for my main formula, I can always rewrite it. I can solve for force knowing that would be work divided by distance. I could solve for distance, knowing it would be work divided by force. This is a simple algebra. So one last concept. Sorry, Emily, was in your way?
Yes.
Came in your way now.
I actually gotta copy that down now.
It's still going to be up here all period.
Oh, okay.
Roberto, can I help you?
I was going to ask you if you already sent the recommendation letter.
No, I haven't done it yet.
Can you please do it before 5? Sure.
I'll try. I can't guarantee it.
Okay. Thanks.
Everybody got this?
Oh, crap.
Now, units. Force we came up with is in newtons. Distance is in meters. What unit do you think work would be in?
Joules.
You looked ahead. Technically, work, since it is a unit of force, newtons, and a unit of distance, meters, technically work is in Newton meters. However, the unit Newton meters comes up in several other forms of energy that we will be discovering later. And this gives us a way to put it. Newton meters
It's joules, right?
is called joule. Joules.
Joules.
It's called joules, and you can use a capital J. So you can, after you get a number, when you calculate work, say work of 10 joules, you can write it as 10J or 10 Newton meters. I prefer this one. This one is nice to know. The unit plays later. But later on, as we study other concepts, potential energy, kinetic energy, we're going to discover by converting them into joules, we can compare energy that's being used in different systems. Does anyone have any question on this up here? You can always come up later and click this if you need to look back at any of the other slides. So for today, scan through the ebook work. There's a video in there that will tell you exactly pretty much the same stuff I told you now. Then you have a worksheet, an online worksheet. I believe it's 15 questions, somewhere around there. They're pretty simple because it's really simple math if you got the formula. And you'll have 2 attempts at it. If you finish early and you owe me any work from this week, I will take work from this week. You need to catch up on this week before I will take any other old work from the last 9 weeks from you guys. I don't want you to fall behind. A lot of people just jump back and try to do old stuff and then they end up failing this week. Any questions on what you need to do for the rest of the period?
Yes, sir.
Okay, have at it. Help each other out. I'll be wandering around looking like an adult answering questions.